Okay, well, another good day of programming paradigms. Now, I think at the end of class last time we were doing passing functions as parameters. Is that right? Don't everybody speak up at once. Anyway, so, and we had just done this together copies of, right? And do you remember how that worked? It was combine is the function, right? And in this lambda combine, was that an actual parameter or a formal parameter?
Formal parameter. That
was a formal parameter. And then down here when we defined power, it was together copies of, and then we passed the multiply function as the actual parameter to the formal parameter combine, so that up here this combine it's left parentheses combined. So that's like saying left parentheses times, when we pass that times as the parameter. So these are called higher order procedures. Now, the next one that we want to look at is this one, define num digits in satisfying. Now these are really long names. Num digits in satisfying. And here's what we want. What we want to have happen is we want to have we want to write a function named num odd digits. All right? Named num odd digits. So that if you do this, num odd digits, and you have like 57,823, this would return what? What would we want this, if we put this in, what do we want this to return? Obviously. 3, right? This will return 3 because there's 3 odd digits in here, right? And I think you actually, didn't you write a program? I think you had an exercise where you did this. So this is an alternative way to define num odd digits. This is going to be a more general way. In fact, not only are we going to write num odd digits, we're going to write something like this, num sixes. Num sixes. And if num sixes was 5, 6, 2, 6, 1, then what should this return, obviously? 2, because there's 2 sixes. So do you see that the only difference between num odd digits and num sixes is going to be what? The what? What kind of digit? Yeah, and what will we do? What will determine what kind of digit it is? It will be a what? Starts with an F. Starts with an F. What paradigm are we in? It will be a function, right? Are you with me? So if we want to define num odd digits, then what will we pass? What will we pass num digits in satisfying? Because look, what is the parameter list of num digits in satisfying? What is it? It says lambda what? N and test. Now, is this n actual parameter or formal parameter? Formal. And what about test? Formal. So when we do num odd digits, what will we pass as test? And what function will we pass? I think we've actually seen it before. Yeah, don't we have a function named odd? Have we used odd before? Yeah, so we'll pass that function on. And if we want num sixes, what will we pass? A function that returns what? Well, it has to return true or false. It's going to be a predicate, so. True if it's what? Equal to 6. That's the function that we will give it. Are you with me? Okay, so, but in general, actually, let's go ahead and let's go ahead and say, according to this specification, num digits in satisfying lambda n test. What is the definition of num odd digits? Can you write this? Can we write this now? I mean, without actually looking at how it does it, but just knowing what it does, not how it does it. Can we write down the definition of num-odd digits? Can you tell me what that would be? The definition of num-odd digits, what would you say? The definition... Wait. We want to define num-odd digits. So it'd be parentheses what? Define num-odd digits, and then what would it be? No. We're not using lambda anymore. Instead, we're doing what? Because what does this return? I'm sorry, what does this return? Yeah, so what will it be? Num-odd, oh, sorry, you were right. Okay, so it's define num-odd digits lambda n, but then what is lambda, but then what is the function? Instead of actually going through and writing the function ourselves, what are we calling? Num digits n satisfying n, and we're giving it what? Odd. Yeah, my mistake. Are we good? Is everybody clear? Now, the question is, how does num digits n satisfying do its job? Well, look. What does it do? Oh, this one is a very robust function, because what does it test for here? The first thing it tests for is if what? If n is what? Yeah, so if it's negative, if it's negative, what does it do? It calls itself doing what? Negating n, and then with the same test, right? On the other hand, if it's less than 10, then how many digits? Then we know if it's less than 10, it's what? It's either 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. So it's one of those digits. It's a one-digit number, and so we say what? If what? If the test of n is true, then what do we return? 1. Otherwise, what do we return? 0. Are you with me? If the general test is 1, otherwise it's 0. But now, if it's not less than 10, then it's what? It's greater than 10, and it has at least how many digits? It has at least 2 digits. So then what do we return? Well, it all depends on what the remainder of n divided by 10 is, right? So if the what? If the remainder of n when you divide by 10 does pass the test, what do you have to return? 1 plus the quotient divided by 10, right? Otherwise, you just return num digits n satisfying the quotient of n divided by 10. Right? Is everybody good on that? So now, how would you define num sixes? Now, this is cool. Do we have a do you suppose there's a num sixes function built in to Scheme? Probably not. So how would you define this? How would you define it? Define, okay, so here, can you predict? Yeah, let's see if we can predict. Define, okay, here. Define num sixes, and then lambda n. Lambda n. And now what? Yeah, num digits in satisfying, and now what do we put? N. But now what do we put? Now what do we put? Ha-ha. What is it? What is its type? Oh, come on, you guys. This is the functional paradigm. What is the type of the thing that we have to put in here?
Function.
A function. So because the type that we have to put in here is a function.
Equals.
No. No, not parentheses, not equals, not parentheses equals. No, test is the formal parameter. Oh, somebody out there can help us? In video land? Somebody come from the future and help us out.
Equals.
No, no. What is the type that we have to put here? It's got to be a function. Oh, come on.
Define a new function.
What returns a function? Oh, come on, you guys. What is the function that returns a function? We should know this by now. Oh, lambda. Are you with me? It's lambda. Is everybody clear? So what should that be? So what should that be? That next one should be, maybe if we put it on 2 lines here, this is n. And then what? Lambda what? And now what is this function supposed to return? True or false, depending on what? Depending on if it's a 6. So how do you so how many parameters does this function have? 1. And then I forget what it's going to be called. And what will return true if it's 6? Oh, come on. Equals.
Whatever we're going to call it.
Yeah, equals. I forget what this letter is. Lambda x maybe, or maybe m. I don't know. Lambda x, and then what is the function? Equals x6. Is everybody with me on this? Oh, they use the same. They use the n. We reused n again. All right. This lambda n equals n6. We could have done it this way. Okay. Is everybody with me on this? The lambda is the function that returns a function. Are you with me? So we needed a function to supply this formal parameter, test. And in this case, the function was built in. In this case, we built it on the fly. Are you with me? Is everybody good with this? All right. You know, I think I could load this code up and just do, you know, nummod digits, but you know I don't think I'll take the time. All right, you guys don't need that demo, do you? Okay. Now, our next topic. There are in computer science a few really, really basic, fundamental, well-known, famous theorems that every computer scientist knows. And one of the really big ones is one called the halting problem. Has anybody here had the automata theory course? But I know some of you will. And if you do, you're going to see this again. It's so important. And what we're going to do now, then, this will be an introduction to this very famous and important problem. It's called the halting problem. And here, let me introduce it this way. And I know you guys have all experienced this. Have you ever been on your computer doing something, and then you click a button or, send something or receive something or do something in a word processor or whatever. And pretty soon your computer, kind of like freezes, and either the little spinning beach ball or the little hourglass, and what happens is you're waiting there for it to finish what it's supposed to be doing, right? And what's always the problem?
Impatience.
Well, yeah, but
Slow.
how do you know if it's just slow? What's the big question? What's the big question that's always lurking in your mind?
Was it a freeze?
And that's the question. Did it crash? Is it in an endless loop? And have you ever had the situation where you thought it was in an endless loop, but then you were just about to stop it, but then, it finished. It finished the loop. You know that feeling? That feeling is at the heart of the halting problem. Because look, how can you know that when you execute your program that it's in an endless loop? You might just be impatient. If you wait a little bit longer, it might finish. It might halt. Are you with me? It might halt, and then you go back to your computer and keep doing other stuff, right? But you don't know. Maybe there's a bug in there, and it's going to go on, and no matter how long you wait, it's never going to halt. Do you see what I mean? And do you understand then that there's no way to figure out by running your program if it's in an endless loop or not, because it might end if you just wait long enough. I'll just wait a little bit longer, but how much longer is a little bit longer? You don't know. All right. That's the problem. So now, let's imagine another scenario. You graduate from Pepperdine, you get a great development job working for a company, and this company makes compilers. All right? And you're sitting at your desk and you think, darn, this thing keeps running and I don't know if it's going to end or not. Maybe it's going to halt, maybe it's not. So, you turn off your computer and you run to your boss and you say, hey boss, I got a great idea. What let's do is, let's write a program that will figure out if another program has an endless loop in it without having to run the other program. We'll just analyze it. You see what I'm saying? Wouldn't that be a great compiler feature if when you compiled your program, if the compiler said, whoop, your program has an endless loop. Wouldn't that be a cool feature?
Yes.
So you go to your boss and he says, oh, that's a great idea. Get to work on it right now. And so you start working on this problem. All right? That'd be a cool feature to have, right? Okay, so here's the halting problem. Is it possible to write a program that does halt, that can determine whether any other program would halt if it were executed? Do you see what I mean? Yeah? Do you see? Okay. And what do you suppose the answer to this question is? Do you think? You think it's possible? The answer is no. You're right. But now, can you prove that it's impossible? Not only can you, but you will. Yeah.
It's possible for us as humans to look at a program and know that it will never.
That is a very good observation. So it does actually, when you think about it, it might seem feasible. That is a good point, and we need to talk about that. Because look, here's one. This function says define return 7, lambda, no arguments. And what does it return? 7. Now, you don't have to run this program to know that it does what? That it halts. Right? Here's another program. Here's another function. Define loop forever, lambda. And what does it do? Loops for, it calls itself recursively over and over and over again with no base case. You can detect, we just analyze this, that it's not, that it's endless. It's like an endless loop. It's endless recursion. So if we can figure it out, why can't we automate that process and write a program that'll figure it out? Seems like we should be able to, maybe. Are you with me? Do you see? Because if we could figure it out, maybe a program could figure it out.
How about something where you go through a loop 5 times and check to see if the values are the same in the last 5 go-arounds? And if they are, then you just assume...
Oh, the state. Yeah, you would check the state to see if the state ever changes. Yeah, of course, that would be a runtime test as opposed to a pre-analysis.
Okay.
Yeah, so that's a different, yeah, you wouldn't want to release that kind of product. Well, maybe you would, into the commercially, like if, well, I mean, can you imagine every single loop in your word processor application would have all these huge tests and test the state? You have to test all the
Well, no, it's just at the very beginning to see if, and then you get rid of it afterwards.
Oh, you mean would analyze?
Yeah.
Would analyze if the state could change. Yeah. See, it is kind of feasible, isn't it? Yeah, maybe we can. Maybe you should get to work on that right away. Actually, if you can do that, you bring it to me first. No, actually, this one I know you can't do.
Oh, okay.
Because we're going to prove it. All right? Now here, you guys, here's the thing. There are a few things in the courses that you take where I'm going to tell you ahead of time, you have to know how to do this. This is one of them. I promise that this will be on the next exam, the midterm. This whole proof. You need to be able to state the halting problem and prove it. Prove that it's undecidable, that you cannot do this. So listen up. As we go through this one is important. This one is so important that you have to know how to do it. You have to know how to prove this one. And you might as well just learn it. You might as well just know that we're going to do it and do it. That's how important it is. So here, what we have is we can figure out that return 7 terminates, and we can prove that loop forever doesn't terminate, does not halt. So now here's the question. Now, we're talking about functions that take functions as parameters, right? So here's what we want to be able to do. Do you see this function named halts? And it's halts, question mark? So that means it's a what? It's a predicate. What's a predicate? A function that does what? Returns type Boolean. Yeah, so it returns type Boolean. So we're going to, and so now this halts has a bug in it, because this halts takes alpha as a parameter, and alpha is a function, and what should it do? It should return true if alpha will terminate, if alpha will halt, and it should return false if alpha won't halt. So there's a bug. It should return true if alpha halts, otherwise it should return F. But it was very difficult for me to write all the code to do that because it'd be very complicated. So that's just as an example, right? Okay. And so now what should happen? What are we claiming should happen? We are claiming that halts return 7 should do what? Return true, and halts loop forever should do what? Will return false. Does everybody see the problem? What we're up against. This is what we're up against. And now, I tell you guys, this particular proof using scheme is so neat. When I first saw this, I was so excited, because when in your automata theory, you'll learn more conventional ways to prove that the halting problem is undecidable. But this is a really slick, this one is a really slick one, and it's based on the fact, look what it's based on. It's based on the fact that it's possible for us, this return 7 is the actual parameter, and it's a function, and the formal parameter is alpha. Yeah? Okay, so it's an easy way to understand the problem. So here is the proof that the halting problem cannot be solved. It's proof by contradiction. So do you remember how proof by contradiction works? Kind of, vaguely. Okay, so what we're going to do is we are going to assume that it is possible to write halts and show that assumption leads to a contradiction. Are you with me?
Yes.
We're going to assume that it is possible to write halts, and we're going to show that it leads to a contradiction. And what do we mean by, we're going to assume that instead of having a bug here, I could put some code here, and it would return, if I put return 7 in, it'd be true, and if I put loop forever, it'd be false, right? We're going to assume that you can do that. Okay. Now here's what we're going to do. We are going to construct another function, scheme function, called debunk halts. And what do you suppose debunk halts is going to do? It's going to be a tool for us to debunk the fact that it's possible to write halts. Okay, now check it out. And here it is. And by the way, all these scheme functions you need to be able to reproduce in the proof. These scheme functions are parts of the proof. So in your proof, when I ask you to prove it, you need to define this, state that we know that this, does halt. We need to be able to write loop forever and know that that halts. And then the question is to define halts that works this way, okay? But for any general one, all right? So now, here's the code for debunk halts. Now, you guys, watch this. Look at debunk halts. First of all, how many parameters does it take?
0.
None. It simply does what? It says, if what? Halts. And now what is the parameter? Debunk halts. Wait a minute. What's it doing? Well, is it? No, because it's analyzing itself in itself. Are you with me? Is everybody clear on that? And if halts debunk halts, what's it going to do? If that's true, what's it going to do? Loop forever. Otherwise, what's it going to do? Return 7. And loop forever is this. See, you see how this loop forever is this, and return 7 is this. Are you with me? So that's how we're going to construct debunk halts. Right? Now, now what we're going to do is we're going to analyze this debunk halts, right? Because by the way, what are we assuming here? What did we say we were assuming? We were assuming what? It's what? Possible write halts. So what are we doing? We're assuming that we wrote halts, and then we're going to use it here in this debunk halts. Are you with me? Do you see? There's halts. We're assuming that we can do it. Yeah? Are you with me? We're assuming that we can do it. So we assume that we can do it. We'll put it in there in debunk halts. Okay. So now there are two possibilities. Now check this out. What's going to happen when we run this? There are two possibilities. Here's one possibility. Now, one possibility is that debunk halts actually halts. Now follow this reasoning, you guys. If debunk halts, what does that say? And if we did write halts such that it correctly was able to analyze it, what would happen? So if debunk halts really does halt, then what does that imply? That halts debunk halts will return what? Well, that what will halts debunk halts do if debunk halts actually halts? What will it return? It will return true. So halts debunk halts will return true. Are you with me? By the way that we, okay, because we're assuming that halts works, that you can write halts, yeah? Okay, but on the other hand, if that returns true, what does that imply? That what executes? Yeah, but that implies that loop forever executes. But wait a minute. If loop forever executes, we know that loop forever does what? It does not halt. All right? But if that does not halt, that means that that's inside debunk halts. That means that what? That debunk halts itself what? Does not halt. So that's a contradiction. Are you with me? Does everybody follow that?
Couldn't you use a different function instead of loop forever that would terminate it? Like why?
Yeah. But what I'm saying is we are constructing, if in fact, that's a good question.
Because like you're assuming that loop forever is the only thing that you would use there. But like if you use like.
Yeah, well, yeah, oh, okay, yeah, I see.
You know what I mean?
Yeah, but what I'm saying is, the logic is going to be this. If you claim to have written halts, this construction shows that that's impossible. Because if you were to write halts, I will give you this specific debunk halts that shows that that's mathematically impossible.
What are you expecting it to return? What do you want it to say?
Well, all I'm saying is this is a contradiction. If we assume that halts could be written, by the way, this is just the first possibility. This is possibility A. If we assume that halts could be written, was written, then this debunk halts proves mathematically that it leads to a contradiction. See, actually, let's come back to that question. What's the other possibility? Maybe we just did not consider the two possibilities. Maybe if we consider the second possibility, we'll have some consistency. What is the second possibility? The second possibility, B, is going to be what? Halts what? Does not halt. Okay, so the other possibility is B. Debunk halts, does not halt, right? But now if you claim to have written halts correctly, are you with me? Then what will it do? Halts, debunk halts, will return false. Right? So that implies that halts debunk halts returns false. But if halts debunk halts returns false, then debunk halts will do what? Return 7 and halt. Right? Because we are claiming that halts itself, now remember, we are claiming that halts itself has to terminate. Let's go back to the original statement. Let's go back to the original. Is it possible to write a program that does halt? I mean, if the program to determine whether another program halts or not doesn't halt, then you haven't, I mean, that's not an interesting problem. In that case, it would just run the program and you'd be left waiting on, you'd see what I mean? So, but on the other, but that's an important point. All right, so let's go back to B here. Okay, so if you've written halts correctly, it will detect that this what? I mean, if debunk halts does not halt, it will detect that this does not halt, but then it will execute return 7, but then return 7 executes, but then after return 7 executes, there's nothing more to do, and debunk halts does halt. Is this convincing? That also is a contradiction. But there's only two possibilities, right? Either debunk halts this function right here, this debunk halts, either it will halt or it won't, right? And this proves that if you claim to have written halts, you can't, it's impossible to do that in general. So here's the conclusion. The assumption implies a contradiction in all possible scenarios. Therefore, the assumption is false, and it is impossible to write halts. But you still have you made a good point. We can look at some programs and figure out whether they halt or not. The question is, can you write a general program that will take any other program and will detect whether or not it halts? The answer is you cannot. You cannot do it in general. It cannot be done in general. Are you with me on that?
Can it be done for a certain type of program?
Maybe if you restrict, maybe if you restrict it to for loops, and you know that and you restrict and you say only restricted ones you could. But you can't, there's no way to do it in general. If you place restrictions on it, then maybe you can. But anyway, this is a very famous proof. It's a very famous problem, and this is a nice proof that fits in with the idea of higher order procedures, where you are passing a procedure as a parameter or a function as a parameter to another function, because that's the kind of thing that you need to do in order to envision the possibility of writing halts that would give us something that's useful. But it turns out to be impossible. Okay, and just to show you here, let's do our first demo. Just to show you that how feasible this could be, let's do this. Okay, so here's our demo, and here is the actual code that we talked about on the slides up there. And notice here, it's define return 7, lambda, no parameters, 7. Define loop forever, lambda, loop forever. Define halts, lambda alpha. This has a bug in it. Now you see why I couldn't put the code in here, because I just proved mathematically that it's impossible to do. Anyway, so, and now, but look, define debunk halts, lambda, if halts, debunk halts, loop forever, return 7. So check this out. If I do run, boom, everything compiles. It's all, you see, it's all great. And here, just to show you, if I do return 7, what happens? 7, right? Shall I do this? Shall I do that? I don't want to do that. Because what will happen? Yeah, I don't want to do that. Okay. What do you suppose would happen if I do, and now, what happens if I do halts? If I do halts, return 7, return, return, if I do halts, return set 7, what do you suppose will happen? True. Unfortunately, if I do halts, loop, forever, what will it return? Unfortunately, what will this return? Oh, come on, you guys. Yeah, because, it just returns true, right? Now if halts really were possible and it worked the way we hoped it would, should return false. But, I can't write it because it's impossible. It's mathematically impossible to write it. You see what I mean? And here, with this particular bug in my halts, what would happen if I'm not sure I want to do this either. What would happen if I run debunk halts? What would happen? Yeah, unfortunately, it will loop forever because when it calls halts, debunk halts will return true, and it will execute loop forever, and then it will loop forever. So I don't want to do that. Too bad my halts doesn't work, but it can't. All right. So that's our proof that the halting problem is undecidable. Now, the next thing that we want to do is more high-order procedures. So now, we're going to talk about procedure factories, okay? Now, what does a factory do? It makes things, that's exactly right. And so what do you suppose a procedure factory makes? It makes procedures. Yeah? Now, the way we're going to illustrate procedure factories is we're going to illustrate a factory that makes a couple, that makes procedures. And if you go to this factory and you give it some information, it will make the procedure that you want. Now look, here is a function called double. And obviously here, you can tell here, double 4, if we have this procedure called double 4, we want it to return 8, double 5, we want it to return 10. There's another function that we want to name triple. And we want triple 4 to return 12 and triple 5 to return 15, right? Now, if I asked you to write double just from scratch, you could do it. And if I asked you to write triple just from scratch, you could do it. But instead of going that route, we're going to have a factory that produces this. And instead of you writing it, you just do what? You just go to the factory, and the factory will return the function for you already built. Are you with me? And the factory is going to be called make multiplier. Because really, what are you doing with this? What are you doing with the double function that you want the factory to give you? What are you doing? You're multiplying it by 2, and then what are you doing with the triple? You're multiplying it by 3. So here we have this. So instead of saying define double lambda, are you with me? Lambda blah 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 blah. You're just going to say, oh, make multiplier. Now, you guys, this is a little bit different from what we did before. Before, what were we doing? We were giving the procedure, passing the procedure as a what? As a parameter. But now, what is this factory going to do? This factory is not just going to, it's going to take in, here, what is this factory taking in here? It's taking in a number. This factory here is make multiplier is taking in another number. But now what is it doing? It's taking in a number, but what is it doing? It's returning a what? No, it's not returning a number. Make multiplier 2 is returning a what? A function. Because when we say define double, this is returning a function. Are you with me? Now, are you with me on that? Okay? So look, this is, let's define make multiplier, right? Now, do you see what make multiplier has to do? If we give make multiplier a parameter 2, then what does it have to return? No, it doesn't return 2 times anything. What does it return? A function. It has to return, yeah, this is a functional paradigm. It returns a function. So now let's do this line by line. What's the first thing that we do if we want to define make multiplier? Tell me what the first line should be. Define make multiplier. Good. That's good. Okay? And now tell me, according to this usage up here, how many parameters does make multiplier have? 1. So what's going to go on the next line? Lambda. And we're going to call it scaling factor. Now, if we can just get this next line, we'll be home free. Yes. Now, why did you hear that? The next line is going to be another what? Lambda. So now, and it's going to be lambda what? What does it have to return? Yeah, but what is the function, and what is the function going to do?
Multiply by
It's going to multiply
scaling.
by scaling factor. But now what's going to be the code to do that? Lambda, yeah. So here we have lambda scaling factors. Can you see what's going to happen? Scaling factor. Okay, lambda, parentheses scaling factor. But now you're saying it's another lambda. Lambda. But now how many parameters does this lambda have? Let's go back one slide. Double 4. Are you with me? It's going to return a function double with one parameter. Are you with me? You see? Does everybody see what it's going to be? So it's lambda scaling factor. So now what will this lambda be? So this will be lambda what? Yeah, some variable. Okay, lambda x.
Parentheses
And parentheses what?
times
X.
scaling factor.
Yes. Parentheses times x scaling factor. Now look, does everybody understand lambda and how that fits in with this? Higher order procedures. All right, good deal. See you next time.